Bismillah ar-Rahman ar-Rahim. Good evening, everyone. Thank you, Dr. Khalid, for your kind discussion. It's so fruitful for us. Thank you, Dr. Shaima, for coordinating such webinars that is helpful for all nuclear medicine specialties or specialists. Today, I welcome you all for this webinar. It will be on bit physics and basic principle. This lecture is designed specifically for junior nuclear medicine physicians, physicists, and technologists who need to understand the fundamental physics governing the positron emission tomography. This is one of the most powerful imaging modalities in nuclear medicine today. Over the next hour, we will build your understanding progressively, starting with basic definition, moving towards practical applications of BET and clinical imaging. Our objectives are as follows. Basic principles of BET, then for the BET operation, the detection system in BET, the fundamental limitations of BET, and the image reconstruction. Then moving to the correction on BET imaging, and finally we will end with the optimization on BET imaging. Okay, so the first question, what does BET stands for? BET is the acronym of positron emission tomography, and it is a three-dimensional molecular imaging modality. Unlike SPECT, which relies on physical collimation, BET uses what's called electronic collimation based on coincidence detection. This fundamental difference gives the BET superior sensitivity and better spatial resolution. This slide is the conceptual heart of BET physics, so I'm going to walk through it carefully. Everything in BET, every image we produce, every count we detect, and every artifact we correct for originated from the annihilation reaction. When we inject the proton-rich radionuclides such as fluorine-18 or gallium-68 to the patient, the nucleus becomes unstable. To achieve its stability, it decays by positron emission. A positron emission is simply a positron is the antimatter counterpart of the electron. So the electron positron is the same but with different charges. It has the same mass but opposite charge. The positron doesn't travel far after this after injection. So it slows down due to some column interactions with the orbital electrons in the surrounding tissue of the patient tissue, losing energy through multiple collisions. This path is called the positron range. And it's typically from 1 to 3 millimeter. We can see it here. I will get a pointer. This is the positron path, okay? And it ranges from 1 to 3 millimeters. It depends on the radionuclide. So for the lower energy positrons have shorter range and vice versa. For example, for fluorine-18, it has from 0.6 to 2.4 millimeters. Gallium, 0.9 millimeter. Rubidium, which is high energy, is the longest, which is 5.9 millimeter. As regards to the tissue type, denser tissue stops positron more quickly. After the positron has slowed down near zero here, so near zero kinetic energy, of course, it meets an electron from the surrounding tissue. When the positron meets this electron, they will annihilate. And this is the annihilation process, producing two opposite photons of 511 kilo electron volt, which we will use later for coincidence. This is an animation showing the annihilation process. As you can see, the positron interact with the electron, producing annihilation pair, and then producing two opposite photons 180 degrees apart. So what's next after annihilation happens? when two opposing detectors simultaneously detect the two annihilation photons, the scanner assigns what's called the line of response. We will call it LOR. Line of response is the line connecting these the both detecting photons at opposite detectors. The annihilation occur somewhere along this line, but we don't know yet exactly where it is. Inshallah, we will address it in the image reconstruction. BIT uses what's called electronic collimation. So electronic collimation depends on two factors: the energy window, and the time window. Energy window make it accurate to collect only photons with 511 kilo electron volt with an energy window, plus or minus energy window, and the time window only detect those photons arriving in certain window, which is certain time frame. It's in nanoseconds, and we will explain it after that. In this slide, we can see the difference between the regular collimation and the electronic collimation. The regular collimation, of course, for SPECT, and as we know, all the SPECT has a collimator. The collimator is made of lead or tungsten and has some holes. Between holes are septa. These septa attenuate all photons that is coming from different direction that is not in the forward direction. So it attenuate all other photons. So it decreases the sensitivity and make it a limiting factor. For BET, no, it's now we have 3D BET. We'll explain all of the types later. So it has higher sensitivity with no collimators. Instead, they use what we call earlier the electronic collimation, which is having the energy window and the time window, as we said. The energy window typically is set around 511 kilo electron volt, like we said, with acceptance window from 400 to 650 keV to allow for energy resolution, the energy resolution limitation in the detector, while still rejecting photons that have scattered or lost significant energy. So all photons that is away from this window will be rejected. The coincidence time window typically from 4 to 12 nanoseconds, depending on the scanner, and it is very, very critical in detecting the coincidence or aligning the line of response. This narrow window ensures that two photons detected simultaneously truly originated from the same annihilation event, not from separate events that happen to be detected nearly simultaneously. Now we will address what we hear about in everywhere regarding the BET imaging. What is a true event? What is a scatter event? And so on. So we need to address all the types of events that may occur in BET imaging. Not all coincidences are detected in BET and are valid data representing true tracer distribution. In fact, the raw data contains a mixture of true, scattered, random, and multiple events. Understanding each type is essential for applying appropriate corrections. A true event results from detection of two annihilation photons from single positron electron annihilation, with both photons reaching the detector without interacting with matter at all. It has some characteristics, such as it originated from the single annihilation. Neither photons undergoes Compton scattering or photoelectric absorption. It is detected within the coincidence time window. Both photons within the energy window only contributes for 30 to 50% of the detected coincidences in typical BET scan. Why this is matter? Because true events are the only data that accurately reflect tracer distribution. The goal of all corrections that we will explain later is to eliminate all other contributions rather than the true events. The second one is the scattered event. It arises when one or both photons of the annihilation pair undergo Compton scattering in patient's body or in the detector material before being detected. What happens is one of the annihilation photons strike an electron in the tissue or the detector. The photon loses energy, scattering at an angle, like we see here, this one. The scattered photon is still detected because we have an energy window. The detector records it as if it come from the expected direction. So the main problem here is that the scattered event mislocalize the annihilation, so it gives another line of response that is away from the original annihilation. The frequency of scatter represents from 15 to 25% of the detected coincidences in typical bit imaging. The scatter also depend, as we know, all of us know that the patient size is very critical in this matter. The energy window width, if we increase it, it will collect more scatter. The imaging region, if it is in the central body region, it will have more scatter rather than the peripherals. The random events, also called accidental events, results from the coincident detection of two annihilation photons that originated from different annihilation. So let's say we have positron A and positron B. Positron A annihilate and emitting two photons, A1 and A2. B annihilate to B1 and B2. So by coincidence, photon A1 and B1 arriving at opposing detector within the coincidence time window. The scanner falsely record them as a true coincidence. Why it is matter also? Random event distribute noise throughout the image, regarding image quality and reducing signal to noise ratio. They increase apparent count in low activity regions and can create false hotspots. The frequency of the random event increases with the increasing the injected activity. So more activity will make it higher. The coincidence time window, wider coincidence time window will create more random event. Also singles. Singles A1 and B1 are called singles. Okay, so the rate of random events is proportional to the square of the singles count rate. The last type of event, which is very rare, is the multiple event. It occurs it's like the random if we can compare them like this, but here the bit city detector will decide which photon I will accept as a coincidence photon with the other. So which line of response I will assign for this annihilation. The frequency of the multiple event are less common but more problematic when they occur because the event is completely mislocalized. So he can make this one the line of response, this one the line of response, or this one as a single. Okay, so he has different options to choose from. So this is also, it's very rare, but it is also contributing to mislocalization of the events. Here is a table that compares between all types of events. We can see here the true, scattered, random, multiple. The origin of this one is single annihilation, no scattering. This is single annihilation photon scattered, two different annihilations, and for the multiple is 3+ annihilations. The impact on image, this is accurate localization, we need it. This is mislocalization, like the multiple, and the noise the random will create noise and reduce the contrast. The frequency, as you see, 30 to 50, 15 to 25, 5 to 15, and less than 5. The correction needed for this, for true, we don't need correction. For scatter, we need scatter correction. For random, we need random correction. For multiple, we need event by event rejection. Let's get away from this serious topics. We can relate these events by what's called The Good, the Bad, and the Ugly. So this was a movie by Clint Eastwood, maybe in the 50s, early 50s. So we can relate them by this movie title. The true coincidence will be the good, the scattered coincidence will be the bad, and the random coincidence will be the ugly. Also, multiple will be here. It will be the bad because it creates mislocalization. Now here we come to one of the most important parameter. Maybe you know it or you have heard about it before. It's called NECR. The NECR actually represents a count rate of true events that would produce the same image noise as the measured data, accounting for discarding effects such as scatter, random, and multiple events. So this is the equation. I know that you hate equations, but it is so simple. NACR equals t to the power 2 t to the power 2 over t plus s plus r multiplied k, which is the truths, the scattered, the randoms in the image. So we need to know why we will account for the NACR. Not all institutions, by the way, will use the same protocols. How can we decide? From this one. So from the noise equivalent count rate, we have this relation between the count rate and the activity concentration. The green line is the truth, the orange one is the scatter, the red one is the randoms. So as you can see, the truths are increasing greatly with the activity concentration, creating more count rate, and the optimum points that we can operate our machine at is at this point. Okay, let's explain it briefly, okay? What happens is at low activity, true events increases scatter and random are minimal. So the NACR increases steeply, like here in the blue line. Near the NECR peak, there is a good signal-to-noise ratio. This is the optimal operating point at which the scatter are on the beginning of its line. Also, the randoms are getting to increase, so we catch it here, and at the same point we catch a high truth probabilities. So beyond the NECR, adding more activity increases scatter and random event faster than true events. So NECR decreases with the image quality, the guards despite higher activity. And this is not matching the clinician who think that more activity, better image. This is wrong. Practically speaking, the optimal injected dose for a given scanner is determined by the NECR peak. Doses should be optimized for each individual scanner, not standardized for or across all the institutions. And here is a table explaining the optimization strategies that we can use. We have, if we make the time window wider, it will increase random, and this is bad. Wider energy window will increase scatter, and this is also bad. Smaller field of view may reduce random and scatter, and this is good. Higher injected activity up to the peak increases NECR, and this is good. Higher injected activity beyond the peak will decrease the NECR, and this is bad. So let's move to the operation of PET scanner. PET scanners can operate in fundamentally different geometrical modes, each of which has its own advantages and limitations. Understanding this mode is essential for choosing appropriate protocol and recognizing mode-specific artifacts. Of course, all of us know we have 2D and 3D. 2D now it's not found at any new scanner. It was found in the early GE with BGO detector. They used to use lead septa here, extended between the crystals, so it will attenuate all photons that is coming with an angle. For the 3D, there is no septa, it is retracted, it's not there, and it collect all the line of responses that is in the same two opposite detectors. As we said, the main advantages of 2D configuration are to reduce scatter. Also, it lowers the radiation exposure as it uses lower injected activity because scatter is reduced. And the main disadvantages are it reduces the sensitivity as the septa will attenuate more line of responses or more photons. But the opposite are found in 3D, as it has much higher sensitivity, shorter acquisition time, better image quality as noise is reduced due to higher count statistics, and finally, it is excellent for dynamic imaging due to high temporal resolution. Temporal means with time, okay? So it's like dynamic imaging. It has also some advantages like the increased scatter, disadvantages, the increased scatter, random events, and it requires higher doses for patients. And finally, it requires more complex correction process. Okay, the core of any PET scanner, it is its detection system. Understanding the detection system architecture is essential for appreciating the PET capabilities and limitations. A modern PET detector is a hierarchical system. A hierarchical means it is step by step, all of this are linked from small to large component. So the modern PET detector starts with the single crystal, individual scintillation crystal. It is the smallest component, like we see here. This is the detector block, and it has crystals. This is the crystals arranged in an array. The typical dimensions of the crystal are from 4 by 4 by 20 up to 6 by 6 to 30 millimeters. The materials can be, like we all of us know, the BGO, bismuth germanate oxide, lutetium orthosilicate, and the lutetium yttrium orthosilicate. Depending on the manufacturer, of course. Its function is to convert the two annihilation photons into visible light. We will get back to the same idea of SPECT, by the way. This is the same detection mechanism. It differs from the arrangement of the component after each other. Then moving to the crystal array, like we see here, this is a crystal array. Some crystals arranged in a certain configuration. It allows position determination through the light distribution pattern, which means that all the light come at one crystal will affect the surrounding, and then it will affect the localization of the event. Then the block module composed of multiple crystals blocks combined with the photomultiplier tube. This is a photomultiplier tube, and this is the block of the crystal. We call it detector block. So we know, of course, the BMT will convert visible light to electrical signal and amplify them to act as position encoder also. Moving bigger to the detector ring. The detector ring is typically a ring diameter from 85 to 90 centimeters for most of the scanner. It enables, of course, 360 degrees. Finally, the scanner assembly, which is here. So it's a closed gantry, the covered gantry, and it has a huge number of crystals, reaches from 10,000 to 20,000 per scanner. Here we can see the PET scanner from inside. We will see the detector block are arranged like you see here, around all over the circle of the PET scanner. And this is the detector block. It's not only one, it's 4 detector blocks, each of which are made of two photomultiplier tubes. And this is dimensions of all of what we have said before. The detection system in PET. This is as we said, the same as happened in the gamma camera. So it starts from photon absorption. The high energy photon interacts with the crystal material via photoelectric effect, then electron excitation, and inner shell and electron is ejected to the outer shell, and the outer electron cascade down, filling vacancies, at which light emitted by which called scintillation. The scintillation photon travels through the crystal towards the photomultiplier tube, and at the photomultiplier tube, we can see in the next slide. No, the next slide. I will show it to you. The photomultiplier tube will accept the light as a photocathode, and then by photoelectric effect, um, um, and then creates an electron. This electron will be multiplied by a series of diodes collected at the anode, after which creating a measurable current pulse. Starting from the first one, the crystal should have some properties. The first one is the density, which describes the linear attenuation coefficient. This describes how effectively the crystal stops the annihilation photons. For example, sodium iodide is weak, BgO strong, LSO is strong, so it differs from crystal to the other crystal. The second one is the light output. It describes how much visible light is produced per absorbed annihilation photons. So higher output gets better signal to noise ratio in electronics. Let's, for example, LSO gives 75% of the light output with fast decay. The third one is the decay time, which describes how quickly the crystal stops emitting light after the photon interaction. Fast decay, we will find it here in the LSO and LYSO, the modern bit systems. For BGO, it's very slow. For sodium iodide, it's mildly slow. The bit detectors also, we can see here the different properties of different crystals used, like sodium iodide, BGO, and LSO. The red ones are the good ones, okay? So for the linear attenuation coefficient at 511 keV, BGO is the best. For the scintillation decay, LSO is the best. The relative light output for sodium iodide is the best. Energy resolution for sodium iodide is the best. So why we don't use it? Because of this and this. It has low attenuation coefficient, and it has a very high decay constant. So we tend to use the LSO for most of the modern scanners. Nowadays, we have some, like Dr. Khalid was asking about the new modalities, the new inventions. They are trying a lot of crystals, like lanthanum bromide. This crystal provides excellent light output and the best energy resolution, around 60.4%. Its timing characteristics are also very good. However, it is highly hygroscopic, like sodium iodide, and mechanically fragile. It can be broken easily, which makes it commercially not available up till now. The other one, which is promising, the gadolinium, aluminum, gallium garnet, GAGG. These crystals offer a high light output and better energy resolution, around 8.6% compared to LSO and LYSO, with no intrinsic radioactivity. You may hear that the LSO have intrinsic radioactivity that may affect the image. So this one has no intrinsic activity. We explained this before, the photomultiplier tube operation. So the light photon come here and to the photocathode, creating an electron, and this electron is multiplied until reaching the anode. We need to know something important about the photomultiplier tube, that is, away from its high advantage of having high response speed and high light output, it is not available or applicable for PET MRI. So for PET MRI, the semiconductor device is used in conjunction with the scintillation detector. We have two types now. I think one of them is now obsolete. It was new when I was learning about PET-CT. The avalanche photodiode, ABDs. These were used in early clinical PET MRI with Siemens Biograph. They are compact and not affected by magnetic field, but they have a lower gain and more sensitive to temperature variations, like more than BMT actually. The other one is silicon photomultipliers, SIBMs. It's also known as Geiger mode ABD or solid state BMT. They are now widely used in modern systems, including those of GE Healthcare and United Imaging Healthcare. It offers high gain similar to BMTs, better timing resolution, allowing for time of flight functionality, and are also insensitive to magnetic field, so it's used in PET MRI easily. I will move fast in this part because we have explained it also in the gamma camera before. So the pre-amplifier, the electronics after the photomultiplier will be pre-amplifiers, which the first stage amplification with low noise, shaping amplifier conditions the pulse for analysis, pulse height analyzer, which measures the photon energy, determines the annihilation photon plus or minus the energy window, the timing circuit, which determines the exact moment of detection in nanosecond precision. The coincidence logic, which compares timing between detector pairs, which we call timing window, and the event routing, which sends the accepted event to the reconstruction computer directly. Okay, we have some fundamental limitations in PET. The very famous three are the positron range. We explained the positron range in the early slides, and this positron range happens before annihilation because it's ideally the positron doesn't annihilate immediately after emission. It travels through the tissue, creating some interactions with the orbital electron of the surrounding tissue. The distance will be starting from or ranges from 0.6 to 2.4, or from 1 to 3. We can make it easy for you. It has some clinical implication, like for small lesion, it may be underestimating the size. And for lesion localization, the boundaries appear blurred because it's not accurate. And for myocardial wall motion, it is difficult to detect a motion less than 2 millimeters, which is the positron range. The second constraint happens after the annihilation, which is photon non-collinearity. As we see here, the basic physics stated that they will annihilate in 180 degrees exactly. The actual thing is not that like that. It will range from 179.5 to 180.5. So it has plus or minus 0.5 degrees variation. This small variation will create a very huge distance variation at the detector. So like if we are making a projection like that, the angle here is so small, and it will, at the detector, it will be so large. This can result in 2 to 3 millimeter spatial error in modern scanners, so it has an impact on the spatial resolution of the scanner. The third constraint happens inside the crystal, which is called the parallax error, at which photons from events near the edge of the field of view strike the detectors at oblique angles. Since the depth of interaction within the crystal is unknown, this creates uncertainty of the exact positioning of the LOR. So it may be here or here. So we have difference that can make some uncertainty in localization. So these are the main limitations we can find in PET. Moving to the image reconstruction, which is the hard part of this webinar, giving a set of line of response passing through this, these are the set of line of responses, okay? The blue ones and the green ones. So it will determine the distribution of radioactivity that would produce exactly those LORs. This is an inverse mathematical problem. We know that the projection, which is the detected coincidences, and must obtain the object or activity distribution. Here comes the sinogram. Sinogram is like what we see here. Don't panic. It's actually the LOR organization, which is a 2D representation of where the horizontal, where the line of responses or the annihilation detected along this line of response. So the horizontal axis represent the angle. So this one represents the angle. That shows which pair of detector capture this annihilation photon. The vertical axis represents the radial position that shows the perpendicular distance from the scanner center here to the line of response. So whenever this is the center, and the vertical axis will arrange what is the distance between the center and the line of response from in the axial and vertical, in the vertical and axial alignment. This is actually the sinogram, and this is, like we said, 2D representation of the line of responses, which will let us to create the image later. Okay, we have, of course, we said it before in the gamma camera, we have two types of reconstruction methods, which is filter back projection and iterative reconstruction. You can actually think of the sinogram as the raw map of where the signals were detected from different angles. From this sinogram, we can reconstruct the bit image using those method. For the filter back projection, it is a direct, fast mathematical method which quickly converts the sinogram into an image, which is why we used it in the early bit systems. Its advantages are that it's very fast, simple, quick, and good for visual checks. It has a disadvantage that it creates more image noise and less accurate quantification. So we can't use it for SUV quantification. Clinically, filtered back projection gives a quick qualitative image, but it's not ideal for precise SUV measurement. The OSIM, which is ordered subset expectation maximization, the iterative reconstruction technique, it reconstructs the images step by step, repeatedly refining it while incorporating the real physics of bit, such as detector response, scatter correction, random correction, and all of other corrections. So we can incorporate these corrections inside, like we see here in this figure, inside the reconstruction, so the image will be created free from all these unwanted events. And nowadays, the computers are very fast, so there is no problem with this technique. Now we have another things that we all of us heard about, which is the time of flight. So it's a very easy mathematical calculation. If we consider this is the distance between this detector and this detector is 30 centimeters, and the event happens here, the annihilation happens here. The time of collection of the photon in this detector was 0.25 nanoseconds, and the other one was 0.75 nanoseconds. So the whole distance is 1 nanosecond, okay? So from this calculation, this is a direct relation. This is 3 centimeters, and this is 1 nanosecond. So we can calculate the distance. So the distance for this one will be 7.5 centimeter, and for the other one will be 22.5 centimeter. So why it is important? Now we knew the exact location of the annihilation. Before, we don't have any idea about where the annihilation happens along this line of response. We collect from several angles, of course, but it will not give us the accurate localization of the event. So this is exact representation for that. For the conventional bit, we have a line of response. We don't know where is the annihilation. For the time of flight, we know exactly where is the annihilation. Other than it is in the center, we will find where exactly is the annihilation. So moving to the correction of bit. Now we explain that there is a lot of contributions rather than the true events. The true events is the needed one. We have true, random, scattered, and multiple. So for the other three, we need to correct for. We have also other corrections for dead time. So we'll start for the attenuation correction. The attenuation correction is the main important one that we should look for. As we said regarding where is the raw data of the bit, the raw data of the bit can't be quantitatively accurate without correction for these factors, which is random, scatter, and dead time also. It provides details about the major corrections and how they improve image quality. The first one we will discuss, as we said, is attenuation correction. And it has several characteristics, and it has also two different ways to correct for. Why it is essential? All of us know that 70 to 80% of the annihilation photon are attenuated. Attenuated from where? From the patient body and from the surrounding, if there is a table or the detector material. The attenuation is not uniform since the central rays pass through more tissue than the peripheral rays. So without correction, the center of the image will be cold. So the solution for this problem is to use any source of transmission through the patient's body to be used for correction. For each LOR, the measured coincidence count is multiplied by the exponential of the attenuation along the line of response. It has a very good, very important impact, as we can see here in the left image. This is not a clinical image. After correction of the using the attenuation map and using CT to create the attenuation map, we will find a very clear image free from attenuated photons. Actually, there are two main attenuation correction methods, like I said before, used in BET, the transmission scan, and it was used in the early types of PET scanners. It's a rotating source outside the patient, outside the scanner actually. The detector measures the photon transmission through the patient. Attenuation map is calculated from the transmission data. It used to be time consuming because it takes time to move around the patient. It takes about 10 to 15 minutes for more time for the transmission scan. The CT-based attenuation correction, which is used widely nowadays, it provides the electron density in voxel. Like we see here, this is a tube, this is a detector moving around the patient. It creates a map of electron density, and it's converted as for attenuation correction in the bit. It's much faster. In milliseconds, we can have an image for the patient, around the patient. Also, it's on the same table, so it's very accurate. It provides high quality attenuation map. It can be also, of course, all of us know that we can use it as for attenuation only, and can be used for as an image, anatomical imaging to accurately localize lesions. There are also some other corrections that have to be done, the scatter correction, because the scattered photon creates false line of response that don't represent the true tracer distribution. they add noise, as we said before. Also, the random correction, because random events adds more noise or a uniform noise actually throughout the image, particularly regarding small lesion detection and quantitative accuracy. We have some different types of correction for scatter and random. For scatter correction, the most known one is the photopeak windowing, at which we use a narrow energy window. So instead of using 460 to 600 something, we use only from 500 to 550 keV window, which will reject most of the scattered photon. There are also some techniques uses simulation and iterative techniques to correct for scatter. To correct for random, we have here the time windows. We use a delayed coincidence window. So to correct for that, the most well-known method is called the delayed coincidence window method, at which we simultaneously record coincidences in normal time window, like here, and also record coincidence in delayed window, which is plus or minus 20 of the tau. Tau is the time window, okay? So the delayed window records only randoms. This will collect randoms, and we can easily subtract it from the original one or the first primary one. This will be scaled later and create an coincidence event without randoms. Here also we have detector normalization. This is another correction, or what we call uniformity correction in gamma camera. Okay, so we can relate to them easily. Ideally, it will correct for different sensitivities for all the detectors. In practice, sensitivity varies due to some parameters, like a slight variation in the crystal thickness, so it is not exactly the same. PMT gain variation, so different PMTs have different gains, and it will be corrected easily. Different optical path, so we can have some variation in the optical path of the light inside the crystal. Also the electronics, it has different gains. It's electronics, so it can vary with electricity easily. So the image without normalization gives an artifact called bullseye or a ring artifact, as we know. These artifacts obscure real pathology, actually. For the dead time correction, it is used due to the fact that at high count rate, the detector can't process events as quickly as they arrive. Some true events are lost, which underestimates the activity concentration. So a lot of photons come, the detector can't count them all at the same time, so they reject a lot of counts. It will decrease the true events, which is not good for us. So correction for the detector normalization. We use germanium 68 source. It's like cobalt 57 in gamma camera. It will create a calibration map that corrects for variations in sensitivity across thousands of individual detectors, preventing the ring artifact. And also for the dead time correction, the scanner component for event, the scanner will compensate for events that were missed. So if we have missed count, the scanner will compensate for it and ensure the quantitative accuracy for the resultant image. Actually, it measures both lifetime, which is the time when the detector was active, and then the real time, and then applying dead time formula to calculate true count rate from measured count rate. Here is the real world correction impact. So if we need to know what is the impact of each correction, we will see here. So for the attenuation, we have count loss without attenuation will be 70 to 80%. So this is very huge. For scatter, 15 to 25. For randoms, 5 to 15. For dead time, 5 to 50%. And normalization will create ring artifact. Okay, and here we can see the image quality impact in every one. Okay, corrections shouldn't be applied in random way. It should be applied in certain order. Modern scatter or modern system carefully order corrections starting with the dead time. This is the first one. Then on raw data counts. Then random correction, subtract randoms from the original data. Then scatter correction, subtract or model the scatter. Then the attenuation correction multiply by attenuation factors that we get from the attenuation map of CT or the source. And finally, the detector normalization. After all this correction, we do normalization to have the detectors, like we see here, all of them are blue, not different color. Okay. Then image reconstruction, calibration, and finally the quantitation. This is the pipeline for the correction. I think this is the final one, the optimization in bit imaging. This is a very important aspect that should be taken care of when we are going to find the dose optimization and the scanning quality. Firstly, all of us know that as low as reasonably achievable, which is a LARA principle, is a guiding principle for nuclear medicine. It states that minimize radiation dose to the patient, minimize radiation dose to the staff, don't to compensate or compromise for image quality necessary for clinical diagnosis. The optimization approach should be through the following steps. So determine the NECR, we explained it before, for your specific scanner. Inject activity to reach 80 to 90% of the peak of the NECR. Avoid the region beyond the peak. The impact of the scanner is very important also. So you see here the faster scintillator will have shorter scan time, allowing lower activity, reducing motion artifact, and it will be beneficial for pediatric and repeated oncology follow-up. So this is also very important. So we have two parameters we can deal with, the ALARA principle and the impact of the scintillator. So this is a table explaining the dose image quality relationship. So we have here the injected activity, too low, 1 megabecquerel, 3 megabecquerel, 4 to 5, 7, too high, which is more than 8. The approximate true count for everyone will be explained here. The image quality for the low count will be poor, have high noise, low optimal, acceptable. The optimal is the excellent, high will excellent to good, too high will be discarding because this is beyond the NECR peaks that, like we said before. So a lot of scatter. Here we have dead time and randoms. Here we have the NECR big area. The acceptable one requires longer time, and the statistical noise will be found in the too low activity. Finally, let's review because we need to finish now. Finally, let's review the essential concepts we have covered and also highlight the basic knowledge that we have covered in brief. First, the annihilation reaction. Positron and electron annihilate, creating two photons at 180 degrees. This fundamental physics enables bit electronic collimation, which is superior with superior sensitivity compared to physical collimation. The coincidence detection depends on two main factors, which is the time window, ensuring the true events rejects random events. The energy window will reject scattered photons. The event classification, we have explained the true events, accurate localization, the scattered event mislocalization, random event noise, multiple event mislocalization. Correction is essential. Essential to what? To maximize the true events in reconstruction. Also, the detector physics, scintillation converts visible light, the two annihilation photons into visible light. Photomultiplier convert them into in the photocathode will be light, then electron multiplied, then goes to the detector electronics. applying corrections, and then creating the image by after reconstruction. The fundamental limitations are the positron range, non-collinearity, and the decay time. As we said, correction is very important. Attenuation will create 70 to 80% of photon loss, scatter 20%, random 10 to 15, dead time 5 to 30, and normalization, the detector non-uniformity creates artifacts, so correction is essential. We see here the photon journey from annihilation to diagnosis, annihilation coincidence, sinogram, correction for scatter, attenuation, random, and detector normalizations, which is the digital cleanup. So we will have a very good quantitatively, clinically acceptable image. Thank you. I hope I finish it in time. And actually, it is a huge topic that can't be covered in this small time. Thank you all.
Thank you, Dr. Ibrahim, for this comprehensive and insightful talk. Very nice, very comprehensive, very informative. So, thank you very much.
Any
دكتور
questions?
حسنى، لو عايزة في تعليق يا دكتور حسنى.
دكتور إبراهيم، أنا سعدت جدا بالمحاضرة، لأن يعني it is very 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 يعني
Simplified.
يعني very illustrative، و I think كل الأسئلة اللي كانت بتسأل الناس السنة دي في الامتحانات، يعني لو هم حضروا المحاضرة دي يعني المفروض إنهم يكونوا لقوا كل الإجابات للأسئلة اللي كانت بتسألهم في الامتحان ومش عارفين يجاوبوها.
شكرا يا بروف. شكرا
شكرا
حضرتك.
جزيلا يا دكتور ابراهيم.
شكرا يا دكتوره شيماء.
احنا جالنا بس تو كومنتس. اول كومنت كان بيقول ان هو is enjoying the lecture so much، وان هو بس is waiting انها
شكرا.
تبي recorded. وانا طبعا
طبعا.
I assure everyone انها ان شاء الله recorded وهتبقى موجوده على مواقع الكليه الجامعيه ان شاء الله. في حد بيسأل حضرتك على الكوليميشن في البات والسبكت والمقارنه بينهم وبين الالكترونيك كوليميشن والفيزيكال كوليميشن.
ايه السؤال
ما
بالظبط؟
فهمش الجزء ده.
طيب ببساطه شديده في الالكترونيك الفيزيكال كوليميشن هو ليد شيت. اوكي، ده الكوليميتر اللي مستخدم في الجاما كاميرا. ليد شيت فيه سبته او فيه هولز، الهولز دي حواليها سبته. دي بتلمت الفوتونز ان هي تبقى in the direct direction coming from these holes to the crystal or to the detector. Any photons that is deviated from the accepted alignment of the holes will be rejected. For the electronic collimation, they have two main parts. The energy window, if the photon is not within the energy window of 511 keV plus or minus the energy window used, it will be rejected. If the two coincidences, so we have two opposite photons, if they are not accepted at the same time window, which is in nanoseconds, it will be rejected also. So we have two factors limiting the acceptance of the photons. If they have been accepted, they will create a line of response, which is what we need from the bit imaging.
تمام يا دكتور ابراهيم. هو كان طبعا كان في الاول في بدايات البيت سكانرز كان ال 2 دي اكوزيشن. ال 2 دي اكوزيشن ده، بس طبعا السنسيتيفيتي بتاعته والكواليتي بتاعت الايمجز ما كانتش عاليه زي كده.
لا، هو الصراحه كانت الريزوليوشن احسن، عشان بس نكون منصفين.
ما هو
الريزوليوشن في
عشان
ال 2
بس
دي
كانت
احسن
الماده اللي بتتحقن
بنحن
الاكتيفيتي
عالي.
بتاعتها اعلى. ما هو
بالظبط
انا
بالظبط.
قصدي ما انا قصدي لما اتحركنا ناحيه نقلل الاكسبوجر بتاع العيان، اضطرينا ناخد ال 3 دي اكوزيشن. فال 2 دي اكوزيشن اللي كان باكتيفيتي اعلى، ده خلاص بقى اوبسليت دلوقتي، ما فيش حاجه اسمها كده.
بالظبط بالظبط
طيب
بالظبط. هو
انا
كل
هسال
الكاميرات
حضرتك.
يعني
اتفضل.
كل البيت سكانرز خلاص ما عادش في حد بيشتغل
لا،
بالبيت
ما عادش
بال
خلاص،
2
كله بقى
دي
دلوقتي 3 دي
الا اللي
خلاص.
لسه عنده الجي اي
قديم بقى.
البي جي
اه
او بس.
اه والله البي جي او كمان دلوقتي في منه 3 دي كله خلاص دلوقتي، حتى البي جي او زي الاي
اه
كيو سيريس دي كل الاي كيو سيريز دي كلها بي جي او
بس هو
وشغاله في.
طبعا الكريستال ال اس او والال او اس او احسن بكتير من البي جي اوف
ما طبعا بس كله
كسنسيتيفيتي.
على قد ثمنه بقى، يعني كله على
اه
قد ثمنه يعني.
بالظبط بالظبط.
هسأل حضرتك سؤال، هل في
اتفضل.
زي ما مثلا ما احنا بنقول مثلا في اوبتيمال راديو نيوكلايد، مش راديو فارماسيوتيكال، راديو نيوكلايد فور ريسبكت، هل في اوبتيمال راديو نيوكلايد فور بت؟
هو الموست كومن الفلورين 18 طبعا، عشان
ما هو
التايم
الفلورين 200
بتاعه.
دوت.
ما
اه
هو التايم الهاف لايف بتاعته هي كويسه جدا بالنسبه لنا، لا هي تو شورت زي روبيديوم ولا هي تو لونج. فاحنا طبعا ده بيبقى كويس في التصوير وفي الويتنج تايم. كانرجي هو كله هيستوي في الاخر. طبعا في راديو ايزوتوبس انرجي عاليه بتبقى تعمل راديشن دوزز عاليه للمرضى زي الروبيديوم برضو. انما الاف دي جي هو الفلورين 18 اتس ايديال، هو عامل زي التكنيشن بالظبط بالنسبه للجاما كاميرا.
and I ask my question regarding the energy of the radionuclide itself.
امم هم
على
هو
اساس ان
هم بقول لحضرتك يعني
الفلورين 18 دوت، الفلورين 18 الانرجي
امم
بتاعته 635 كيلو الكترون فولت، يعني
اوكي.
قريب قوي، يعني قرب الراديوكلايد اللي مستعمل في الراديو فارماسيوتيكالز اللي يوز ان بيت سي تي. كل ما تقرب من 511 كل ما تبقى افضل، يعني بصرف النظر بقى
لا
عن
لا معلش
الفاكتورز
يا دكتور،
التانيه.
ال 511 دي بعد ما يحصل انهيليشن، يعني هم كده كده كلهم هيطلعوا 511 كي اي
ما
في.
انا فاهم يا فندم، ما انا فاهم يا
اه
فندم،
اه.
انا
فهو
فاهم
مش
والله.
مش دي
لا انا بتكلم دلوقتي يا فندم، لو دلوقتي احنا بنتكلم على جاليوم 68.
اه اه.
جاليوم 68 الانرجي بتاعته كبيره.
طيب بالنسبه للجاليوم 68
1000
بالذات، انا كان ليا
1900
مشوار
1900.
فيه. بص يا
انا
دكتور، كان
حاسس.
ليا مشوار
طب انا
معاه
بس هقول
قبل
لك
ما.
اوصل لك نقطتي عشان تعرف ترد عليا بس.
طيب
ال
حاضر.
1900 ده ليها باص كبير قوي عقبال ما تعمل بوزيترونيوم.
اه
الباص
اه
كبير
اه اه
دوت
اه
بيأثر
اه.
على الريزوليوشن.
طيب، ما عشان كده احنا قلنا، انا ما قلت هنا في المحاضره ان في ديفرنت راديو ايزوتوبس كل واحد منهم له بوزيترون رينج. اعلاهم كان بتاع الروبيديوم، ليه؟ لان الانرجي بتاعته عاليه. فاعلى بيمشي 6 مللي. 6 مللي ده تو ماتش. 6 مللي، حضرتك متخيل ال 6 مللي دول هيطلعوا يعملوا ديفرنس قد ايه عند الديتكشن؟ كبير جدا مش صغير. يعني احنا بنتكلم في الانجل بتاعت ال 180 بلس اور ماينس 0.5 ديجريز، والكرييت 2 تو 3 ملم عند الديتكتور. فمتخيل حضرتك 6 مللي هيعملوا كام؟ 6 مللي ديستنس بقى هتعمل مسافه كبيره، مثل كوليزيشن كبير. فعشان كده هو طبعا
وكل ما الباص فعلا الباص بيطول، كل ما
اه
الباك بروجيكشن بيوسع الانجل، بيقلل سنه الريزوليوشن السباشيال.
بالظبط. بيبوظوا يعني بيخربوا خالص.
عشان كده انا بقول دايما الفلورين
امم
the optimum radionuclide used with radiopharmaceuticals for BCT، لانه هو اقل فعلا بوزيترون باص.
بالظبط بالظبط. هو عشان كده يعني معظم النيو ريسيرشز كلها شغاله على راديو فارماسيوتيكالز تبقى مع الفلورين. يعني حتى طبعا انا عارف الترند دلوقتي البي اس ام اي والروتيشن 177 والكلام ده كله، بس ده في الثيرابي. احنا بنتكلم في الايمجنج هتلاقي كله منحصر في الفلورين 18 مع ديفرنت راديو فارماسيوتيكالز. يعني هو لازم
تمام.
وانا على فكره اتكلمت في الكلام ده في مؤتمر بتاع الميدترينيان كونفرنس. هم كانوا بيسالوني انتوا عايزين ايه، يعني انتوا عايزين ايه؟ فقلت لهم احنا عايزين راديو فارماسيوتيكالز جديده مع الاف دي مع الفلورين 18 عشان تبقى
صح، اللي هو
الدنيا
الفلورين
سهله.
لانه ده
اه
فعلا اوبتيمال بالنسبه لنا.
اه بالظبط بالظبط.
الهاف لايف كويسه، الباص بتاعه كويس قوي، مقبول جدا، يعني
مش
مش
كبير
مش
اه اه.
مش هيعمل ديسكريشن.
بالظبط
شكرا يا
بالظبط.
دكتور ابراهيم، ربنا
العفو يا
يكرمك.
فندم، العفو.
ومنورنا دايما ومشرفنا،
ضروري،
ودايما
الله يكرمك.
الفيزيكس دايما انا عايز اقول ايه هايبر دايناميك، ودايما
بس
اسئلتها حلوه.
بس تقيله على
اه
الناس
لا
شويه.
مش تقيله والله، يعني
اللي
احنا
عايز
الحمد
يحبها
لله.
يحبها.
اه هي يعني هي دي البيزكس، ما البيزكس
اه
لازم
اه
عشان الواحد يجيب حاجه من جدرها يجيبها صح بقى.
بالظبط بالظبط
آه
كده.
فربنا
احنا ان
يبارك
شاء
لك يا
الله
رب.
هنكمل المحاضرات دي بعد العيد.
ماشي حاضر.
كورس الفيزيكس مستمر معانا، بس
اه
لان احنا عندنا محاضرات تانية الاسبوعين اللي جايين، فان شاء الله احنا هنتوقف عشان شهر رمضان، والمحاضرات بعد كده هتبقى بعد العيد.
إن شاء الله. طبعا أنا أحب أعرف الناس كلها إن في مؤتمر، طبعا لازم نقول مؤتمر الجمعية السنوي ال20 هيبقى في شهر إبريل 12 ل 13 إبريل. وطبعا ده فرصة كويسة جدا لأي حد عايز يبريزنت الأعمال البحثية بتاعته. أي ريكومند إن كله يحاول يحضره إن شاء الله. وطبعا
يا
المحاضرة
ريت
دي والمحاضرة اللي
برضه
فاتت هتبقى موجودة.
فكر يا دكتور إبراهيم تبعت لنا محاضرة حتى ولو مسجلة، لو مش قادر تحضر معانا
إن شاء
للمؤتمر.
الله.
برضو دي فكرة أفكر فيها، لأن طبعا بيسعدنا أن تشاركنا بالمحاضرات في
إن شاء
المؤتمر
الله.
بتاعنا اللي هو 11 و12 إبريل إن شاء الله.
إن شاء الله. طبعا المحاضرات دي هتبقى موجودة على مواقع المجلة يعني موقع الجمعية ووسائل التواصل الاجتماعي زي لينكد إن وفيسبوك والكلام ده كله. فأي هتبقى مسجلة، واللي عايز يتفرج عليها بعد كده يعني براحته، يحاول يفهم براحته. إن شاء الله متاحة هي واللي فاتت إن شاء الله.
دي
وإحنا
صدقة
طبعا
جارية، صدقة جارية يا دكتور إبراهيم.
الله يكرمك يا دكتور، شكرا جزيلا، شكرا جزيلا.
شكرا دكتورة
استنى
دكتورة
حسنى.
عشان خلاص
في
الماتش
حد
بدأ.
تاني عايز يسأل أسئلة
لا،
للدكتور
الكل
إبراهيم؟
بيشكر دكتور إبراهيم جدا، ونستمتعوا جدا بالمحاضرة. واحنا سعداء برضو بحضور الجميع يعني. الحمد لله الحضور كان رائع، وشكرا جزيلا، ونتمنى
شكرا
نشكرك جدا
جزيلا.
يا دكتور إبراهيم.
العفو يا دكتور، العفو. نلقاكم على خير إن شاء الله.
شكرا يا إبراهيم،
شكرا
وإن
يا
شاء
فندم.
الله نلتقي بعد العيد. حضر المحاضرة اللي جاية قدامك وفرصة كبيرة أهو.
موجودة يا
شكرا،
فندم، موجودة إن شاء الله.
ونراك على خير إن شاء الله.
إن شاء الله. السلام عليكم.
متشكرين جدا، سلامة
العفو.
الله.
السلام، مع السلامة، مع السلامة.